Hey, hello. Why YouTube have so long the lag? So YouTube lag for 40 seconds? Okay, yeah, it's back. So today we are going to start the final chapter of the RMO book B. The final chapter may be the most difficult one. It's combinatorics. So actually for combinatorics, we don't expect everyone to be able to solve it. Means, right, if we face a combinatoric in the real test, so normally there are around 1 or 2 questions in each year's RMO or APMOPS. Yeah, feel free to skip it because you fail, everyone else will fail as well. So actually don't mind. Or you can guess the answer randomly if it's RMO. But for APMOPS, it's a short answer, so never mind. You just skip it. Okay, so about the combinatoric, there are actually three typical questions that is often asked. The first type is the constant value problem. So in this question, so we should find a constant value of, right, so maybe some combination or some arrangement, and we use the common value to solve the problems. So how to find this hidden value, hidden constant values? So these are our questions. So now the question 1, yeah, is something that, so we have 888 students standing in a circle. So if any consecutive group of 33 students, at most 9 males around it, so to find the maximum number of male students. So AA8 is not a multiple of 32, or it will be quite easy, right? So AA8 divided by 32, yeah, we should have an answer. So yeah, I don't recall it. So it's 27 and the remainder is 24, which means, right, so we can only have a whole group for the first 27 group of 33 people. So 32 people. So now this is what? So at most 9 times 27. Yeah, it's easy to determine this. But what about the remaining 24? So what about this remaining 24? So can we just, right, because at least at most 9 in all the 32, can we put the last 9 all inside this 24, right? So at most 9 here. Can it be? Actually not. So if they are forming a line, this is the right answer. So if they are forming a line, this is okay. So we just put, so the first 27 group is 9, and for last 24, we make them at most 9. So the answer would be 9 times 28 if it's a line. But this is a circle. So for circle, this one won't work. Because, right, this 9 you put inside the last 24 will influence the first 8 of your 32. So it won't satisfy it. So that's a key point. But how to solve the circle problem? So now, yeah, maybe I write here for line, right? So for line is 27 times 9 plus a 9. So it would be like 252. But for circle, it's not. So for circle, so we should ensure, right? So each from the first to the last, right? They all well. So now we should determine it by calculating a total value of what? So we name it as A1 to A888. So now for each people here, so we name it, we give him the value. So if it's a male, make it into 1. For female, make it into 0. So the value for each is either 1 or 0, and 1 is male, 0 is female. Then if we putting someone together, the sum of them just referring to the number of males inside them, right? So now, according to what's said, so for each consecutive 32, right? The first 32, the sum of it is smaller than 9. And the second 32, smaller than 9. And then we trace back until the last, which is start with A8 until A31. This consecutive 32 is also smaller than 9, no greater than 9, right? Okay, and then we adding them together. So we should notice that we're adding all the 33 groups together. So each number belongs to 32 different consecutive groups. So each number is counted for 32 times. So now the sum of overall is just the 32 times of the sum of all numbers. And this one should be smaller than 9 of the 888. So now we can directly get the total sum of all people, which is referring to the total number of male, should no greater than 9 times 888 over 32. And then this number is, so you check it. It's 249. Sorry. Yeah, 249 and 304. So it's an integer number. So at most is the 249. This is the answer. The key point to solve this question, yeah, actually, we just give value for the male and female, and then use the total sum, right, to get the answer. Now, it's very interesting questions. So know that for line and circle, they're different. For line, we can just make all the group with 9. So last 24 also 9, but for circle, we cannot. So you see that it has 3 less for circle than the line. Okay, now 42 is, now maybe we don't start 42. We move to a very similar question, which is 41. So it's the last question of today, is the question 50. Why 50? Because it's also making some numbers into a circle. But now this is the RMO round 2 question. You need to write proof for this. So it is very difficult. And the logic is a bit complicated, but actually the method is quite similar with the question 41. So it said that we have 26 different numbers randomly arranged. So assuming they being A1, A2, A3, A4, A5, A6, and then to A25, A26, okay? And then he said that, so can we, right? So no matter how these numbers are arranged, so what's value of these numbers? So can we always find there are always 4 consecutive numbers? So the 2 middle have a greater sum than the 2 ends. So for example, A2 plus A3 is more than A1 plus A4. So is that, so no matter what's the number, no matter how we arrange it, there must be such a number. So the answer for this question is yes. But what's the meaning of this yes? Yes is that, so no matter how we arrange it, we can always find. So how to prove it? So to prove this, we want to stand in an opposite opinion. So which is, what if the answer is no? The answer no means that assume, right? So if we have a certain arrangement for us to not finding any of unable in finding such a number. So that means, so for this arrangement, so each of the 4 consecutive numbers don't satisfy the condition, which means that for all the consecutive 4s, the middle sum is always equal or smaller than the end sum, which means, right, then for this arrangement, we must have, for A2 and A3, they must be smaller, or at least equal to A1 plus A4, and A3 and A4 smaller or equal to A2 and A5, and A4 and A5 equal or smaller to A3 and A6 until the end. So the last is A1 and A2 must be smaller or equal to A26 and A3, right? So if there is an arrangement like this, so all the consecutive groups satisfy this condition, let's see what we get. So like the question 41, we also adding them together. So we should get, so let's see, when we add them together, so on the left is all the sum of two consecutive numbers in the middle. So each number is counted for 2 times. So the sum to the left is the sum of all these numbers. What about right? Right is the sums of all this type of numbers, all 2 ends. Of course, each number also served 2 times for each of the pair. So to the right, also each number is counted twice. So the sum to the right is also A1 to A26. So now here comes the thing. So the sum to the left actually is just equal to the right. But if this is, so from all the process, we use the smaller or equal, smaller or equal. And making together, we get an equal. So how to make this equal happen? If we want to make a sum exactly equal, we should make each step be just equal. Okay with this? Because if there is only one step which is not equal with smaller, then the left must be smaller than right. However, we have an equal here. So to make this equal happen, everything here must be an equal. So okay with this? Okay, let's move on. So if we're okay with this, then so that is to say that for each of the two consecutive numbers, the sum of middle two must be equal to the sum of the end two. Let's see. So if we can satisfy this condition, so for each numbers here, for example, right? So now we have A1 plus A2 plus A3 equal to A1 plus A4. And A3 plus A4 equal to A2 plus A5, something like that. So now, to make this thing happen, we made some changes to this forms to make it into a difference form. So which is A2 minus A1, then will equal to A4 minus A3. And here we make it into A3 minus A2 equal to A5 minus A4. Or maybe we reverse it so maybe we treat A2 is larger. So A2 minus A3 equal to A4 minus A5, which is just exactly the same. So why is this? Because now, right, so we can get this conclusion. So now we see A2 minus A1 equal to A4 minus A3. Assume that A2 is actually larger than A1. So we assume that the difference here is an X. So the difference here, A4 minus A3 is also an X. And for the same reason, this is a plus X, plus X, plus X. So all the even terms is larger than the X than the odd term before it, right? And also, right, so A2 is larger than A1. So maybe A2 is larger than A3, or maybe we just assume it larger. So if it's smaller, then there will be a more serious problem. So we see that A2 to A3 is a minus Y, then this is a minus Y. So also, for even to odd is a minus Y. So they are all equal. And we see, so now we form a circle. And in this circle, we start with A1. We have plus X minus Y, plus X minus Y, plus X minus Y. So when A1 is back to the A1 again, so we have experienced 13 of plus X, 13 times of minus Y. And we back to A1 again, which will lead to X minus Y equal to 0 and X equal to 1. So now plus X minus Y referring to 0, which means then there comes A1, so it's actually equal to A3 and equal to A5. So all the odd terms must be equal to satisfy this. However, we should have 26 different numbers here, which means this is not possible. So we assume there is an arrangement here, then we prove this is not possible. So no such arrangement. So there is no such arrangement, which means there must be able to find. Because there is no arrangement that we cannot find. So there must, so for all conditions, we must be able to find. So this is where this yes comes from. A very complex logic, I have to say. A very difficult question. Anyway, this is round 2 question. Yeah. Anyway, this is round 2 question. So I just feel it's similar to the question 1, so I put it here. Okay. Then maybe we're back to some easier questions in front. 42, right? Question 42. So this is something, yeah, also about the constant values. So 6 musicians gather at a music festival. So in each concert, so someone is performing, others are listening, right? So to ensure that everyone must listen to others at least once. So he served as the audience and others served as the performer. For example, yeah, if we have A to perform and B, C, D, E, F is listening, which means now B, C, D, E, F all listen to the A, right? So or we can make A, B performing, C, D, E, F listening. So now C, D, E, F will both listen to A, B, and vice versa. So now if A, B, C is playing and D, E, F is listening, so D, E, F will all listen to A, B, and C. Okay, so the question is, at least how many times of performance need to be held to make everyone listen to everyone else, right? So now first, it's easy to find that if we just keep the first process, so we make A, B, C, D, E, F all perform a solo, right? So 6 performance will obviously help us do it. So the answer must be smaller than 6 because 6 is very easy to find out. So how to get this answer? So now first see that, so we will determine a value. So because we are math, right? The combinatorics is also math. So we should have a calculation. Sometimes we should calculate something and to determine it, right? So now the key point is, so we have 6 musicians and we treat one listening to another called one listening. So we have 6 people and each need how many times for listening? Listening to other 5. Need 5 times of listening. Which means, so totally we should arrange 6 times 5. So totally we have 60 times of listening. So we should arrange 30 times of listening. And then we see we have 3 ways to form a concert, actually 6 ways. But actually, so 1, 5 and 5, 1, 2, 4 and 4, 2, 3, 3, and they're all the same. Which means in a 1, 5, we have how many times for listening can be held in one concert? 5, right? Because 1 times 5. So for 1 to 5, we can create 5 listening. For 2 to 4, actually, we have 8 times for listening. And then for 3 to 3, we can have at most 9 times of listening. So actually, the 3 to 3 is the most efficient way because in each concert, we can have 9 listening. So now, totally, we have 13 listenings. Each concert at most 9. So how many concerts do we need? The 3 remainder 3, so at most, at least 4 of it. So the question is, so how to construct this 4? How to construct this 4? So it's not that difficult. Yeah, I will show you an example. So just write here randomly. So you can check. So first, it's like A, B, C to perform and D, E, F to listen. Or maybe I use this. So D, E, F listening to A, B, C. And then it's A, D, E performing, B, C, F listening. The third would be C is BDF performing. ACE listening. And 4 is CEF performing. ABD listening. Yeah, we will check. So this must be okay for all. So now this example. Yeah. This is the question 42. So question 43. Yeah, this is something that we need to find the constant of the operation. So the operation is that we have number 1, 2, 3, 4, 5 with 2018, 2019, 2020, 2021, 2022. Right? So actually, in each operations, we erase one of the certain number. So we erase 4 of them, and we add in 2 to the remaining one. So actually, in each operation, we have 4 of them get -1, and 1 of them, maybe I write the 4 here, and 1 is a +2. So numbers are handled in a different way. We don't know which is to be removed, which is to be added, right? So then how to do this? Actually, we have 2 ways of doing this. The one way is that, so we want to find, so if there are only 4 numbers remaining, we want to find the 4 numbers. Maybe we just try to get here. So how to get here? So actually, the easy thing is that we want to find a way to reduce the number step by step. So because each number can be added or removed, so maybe we find the pattern of it. So how to get the pattern? So we can just, right? So name this +1, right? So we get the plus on each of 5. Or to say that in each of the 5 operations, so first, we add in 2 ones, remove 2, 3, 4, 5. Then we add in 2 twos, remove 1, 3, 4, 5, right? So if we do these 5 operations, so each number will be added 2 for 1 time, -1 for 4 times. So during this 5 operations per term, so each number must be reduced by 2, right? So we can keep this process again and again. So each time, so 5 operations in per turn. This pattern to make every number reduced by 2. So make it fair to everyone, right? So then after doing this, we would get, so after so many, so we -2 again. So together we minus the 2018. So it's easy to get to 0, 1, 2, 3, 4. Then we start with 0, 1, 2, 3, 4. We now have 10 numbers, so we operated it into the only 4 left. So first, we must add in some ones because we have no ones to remove. So becoming a 0, 1, 0, 2, 0, 1, 2, 3. And then we adding a 2, becoming 1, 1, 0, 2, 0, 1, 2. Yeah, 1, 1, 2, 0, 1, 2. And then we add in 3s, becoming 0, 1, 2, 0, 1. 4 remaining. So this is the answer we needed. Right? So the first method is that, so we just think of a way to do the operation in a pattern, and then we get into the easy situation, then we try the last few steps to get the answer. So the remaining number is 1, 2, 2, 3, and 1, 5, which will lead to the production is 19, right? 19. The production is 19. This is the method 1 by operating. But actually, we have another way, a more mathematical way, is let's write it here. To find the key point, which is we use the remainder. So why the remainder? So look at this. So we have 4 numbers to minus 2, 1 and 1 number plus 2. So what's the common? So is there any common thing between a minus 1 and a plus 2? Because different numbers are doing different operations. But as long as we can find some common things between them, so they can be the same. So minus 2 and plus 3. So plus 3 can be treated as, so minus 2 and plus 3. There's a minus 1 and plus 3. So if we plus a 3, so what is unchanged? The remainder by 3 is not changed. Right? So no matter if we have minus 1 or plus 2, so the remainder of 3 is always a minus 1. So in the mode 3, right, in the mode 3 meanings, minus 1 and plus 2 have the same effect. So that is to say, we can research the remainder of these numbers divided by 3 to find the terms. So initially, 1, 2, 3, 4, 5. Initially, we have 2018, we have remainder 2. And 0, 1, 2, 0, right? This is the initial remainder. So for each step, the remainder by 3 will all reduced by 1. So 2 becoming 1, 1 becoming 0, 0 becoming 2, right? 0 is 3. So then after the first step, we becoming 1, 2, 0, 1, 2. Second step, 0, 1, 2, 0, 1. Third step is 2, 0, 1, 2, 0. And back to normal, right? So 3 step is a pattern. So the remainder of 3 would just repeating in all these patterns. So among all the patterns, so which of it can make the sum of the remaining number be 4? Only this one, right? So only possible way, so can be 4. So now this is the final remainder condition of all the numbers if there are only 4 numbers left. And so the remainder here, 1, 2, 1, will just represent the actual number of the 2, 3, and 5. Exactly what is here. So the answer is the same, right? So if we look at the remainders, we find the minus 1 and plus 2 have the same meaning in the most 3 remainder, then this question will be solved. But actually, I believe for primary school students, it's very hard to think of this method. So maybe we just use the first method. So we find a way, operation patterns to make it into a smaller number, and then we operate it to get the answer. I think method 1 is good for all of you. Okay. And then the question 44 and 45, they are very similar thing. This is about the chessboard dying. So chessboard dying is something that we so grids, right? So if there are some grids here, so we should actually, so we colored some of it into black, others into white, and we use the colored heuristic to help us solve it. So question 44 is a very classic way. So this is often seen in SMOPS and RMO. The chessboard dying, which means it's the adjacent dying. So now here we color the board with adjacently black and white, or in the screen is red and white. So red is black. Okay. So when do we need to use the chessboard dying? Look at this word. As long as you see this word adjacent in the question, and it's also something in a rectangle, yeah, in a square or something like that, right? Yeah, it's often important for you to use the chessboard dying. Okay. Then, after we dye it into the black and white, what do we do? So let's see, so what's the operation we are doing? So in each operations, we are just to pick up 2 adjacent grids, like this or this, right? We just pick 2 adjacent grids to both +1 or both -1. So if 2 grids are During each operation, we have two grid, which must be, where two adjacent grids must one black and one white. So together, +1 or -1. So two numbers +1 or -1 together. So what is unchanged? What's the constant? It's the constant difference, right? So the difference is unchanged. So we +1 or -1 for both black and white, which means during each operations, the difference not only among two grids, it's a difference between all the black and white. It's not changed. So no matter how many times we do the operation, the difference between all the black grid and all the white grid still is unchanged. Then it's easy to solve the question, because if it is unchanged, the difference on the left is same to the difference on the right. So to the left, we have white minus black. It's 81 minus 80 is an 8. What about the right? So in the right, so all the blacks are 1, all the whites are 1 except for this 8. So left to the right, the white minus black then would be coming. So white is 7 plus 8 minus the black 8. So difference is unchanged. So this is still the 8. So then to keep this unchanged difference, A must be. Okay, this question. We use the chessboard dying, and we find that during each operations, the difference is unchanged. Then question is solved. Okay, yeah, this is the question 44. For the question 45, however, so maybe we need to use another way of coloring. So if we are going to find some 1 times n, right? So this 1 times n to fill up it. So this is called the diagonal coloring. Diagonal dyeing, actually. So when do we use the diagonal dyeing? Yeah, mainly for the 1 times n rectangles. As long as we sum some of the 1 times n rectangles, the answer 9. So 9. Okay. So what is the meaning of diagonal dyeing? So for example, here, right, we want to make 1 times 6 and 1 times 7 to fill up 11 times 12. So at least how many rectangles do you need to fill in this, right? So now, firstly, yeah, we don't know how many 1 times 6 and 1 times 7, but yeah, we can solve the equation like this. So for example, we assume that we have 6x of 1 times 6, y of 1 times 7. It's quite obvious that, so if we want to make smaller number use, we want to make 1 times 7 as many as possible, right? X at least as possible. So first we should get, so 6x plus 7y should be equal to 11 times 12, right? So obviously like this. So let's see. So maybe we try to find out, so what's the maximum value for this x and for this y, right? Maximum for y. So obviously, this one is a multiple of 6. This one is a multiple of 6. Then, so x, so the 7y must be a multiple of 6, which is quite obvious. Okay, then, so we just try, so we just try, so 11 times 12 divided by 7. So it's 1, 3, 2, so it's 1 and 8. Yeah, 1 and 8. So actually, so y is smaller than 18 and it's multiple of 6. So it's very obvious that the largest possible value is y equal to 18, x equal to 1. So we can use 1 times 6 and 18 1 times 7 to satisfy the need. So is the answer 19? No, but the answer is not 19. So for this question, there's always a trick. If you easily get the, so this is called the extremum in theorem. Theorem. This is extremum in the theorem, but a theorem may not be reached. So we should check whether we can actually do this. We can use this 19 to fill in. But sadly for that, the answer is no. So how this is not possible, we should use the diagonal dying to help us prove it. So now firstly, the diagonal means that we can color all the diagonals. One of the diagonal be all black. And then, we want to use the 1 times 7 to fill it in. So then we count for every 7 grid. So 1, 2, 3, 4, 5, 6, 7. And we, along with this diagonal, color each of the grid that is exactly 7 grid away with the former one. So 1, 2, the horizontally and vertically, 1, 2, 3, 4, 5, 6, 7 here. So this is called diagonal dying. So we choose a diagonal, then we count for the same length of the 1 times n of the rectangle, and then we color the grid L. So which makes that, so the distance between all the black grid in different diagonals is always the 7, right? It's always the 7. Now, because each grid is 7 grids away, so for each, no matter 1 times 6 or 1 times 7 can cover at most 1 black grid, right? You cannot use 1 times 6 or 1 times 7 to cover 2 because distance is 7. So now the problem is how many black grids are here? So we have 11, we have 5, we have 4. Totally, we have 20 black grids. And each 1 times 6 or 1 times 7 can only cover at most 1. So at least how many do we need? 20. So this 19 here is extremum in theorem. So we calculated it. So 19 is possible for the total area, but it's not able for us to actually fill it in, because fill it in, we need at least 20 1 times 6 1 times 7 to fill all the black grid. So 19 is not okay. So we should find a larger. So the larger is very easy. So we use the crossover the terms. So 18 minus 6 to become here 12. 1 plus 7 to become here 8. And this is exactly 20. So we use 6, 8, and 12 sevens to fill it in. And this is very easy to achieve. Very easy to achieve. So actually, we can use 4, maybe not 6, 7, or 6, 7 may be okay, right? So we can use this 6 sevens, to times 2 of the 7 times 6. And this is 8 of the 1 times 6. So we can make it into 7 times 6 and 1 times 6. And we use this to fill in all the grids. It's very easy, right? So then it will be very easy for us to put it. So it's obviously okay. So I will show you an example. So for example, we can use this is the 6 times 7, right? And we have 6 times 7. So this is this is 6, and so this is 6. This is 7. And then we add in 4, 1 times 6 here to make a 6 times 11. And 2 of the 6 times 11 will make up for 11 times 12, right? So actually 19 is not okay, 20 is okay. So the answer is at least 20. So in this question, we calculated for the 19, but 19 does not help. So almost 20 actually. So, and a similar question is the question 48. We should put them together. So 48 is very similar to it. So we want to fill 11 times 11 with 3 times 3, 2 times 2, or 1 times 1. So what's the minimum number of cases to solve this question? So now the key point is also, right, we use X, Y, and Z. So actually we should have the 9x plus 4y plus 1z equal to 11 times 11 is 1 to 1. So we want to make at most So as many 3 times 3 as possible, as many 2 times 2, as many 3 times 3 possible, actually. But how many 3 times 3s can here be? Actually, so can this like be 1 to 1 divided by 9 is 3? So can we 13 of the 9 times 3 times 3s? No, because firstly, we should put in 3 times 3 in 11 times 11. So actually, we know in a row, right? We can only put 3 times 3 in a row. And also, it's only 3 of the 3 times 3 in a column, maybe not in a column. Or maybe we have to say that vertically and horizontally. Three, 4, at most 3, 4, 3 times 3 to put in. We cannot put 4th, which means, right? So at most, right? So at most, how many 3 times 3s is 3 times 3? At most, 9 of the 3 times 3s can be put in, right? We cannot put more. So firstly, X cannot treat the 13 step. At most is 9, right? So then if we treat this as a 9, then this is a 40. So it's very obvious to get the 9, 10, 0. So the total is 19. The total is 19. So is it possible? So is it possible that we use 9 and so 9 3 times 3 and 10 2 times 2? Can we just exactly fill it in? But actually, if you try, you will find it no, right? So it's 1, 2, 3, 4, 5. So yeah, we can get this 3 times 3 here. But if you want to fill in the remaining, so 1, 2 times 2, 2 times 2, 2 times 2, 2 times 2 times 2, yeah, here comes the problem. So this corner, we cannot fill in it with 2 times 2s. Also 1, 2, 3, 4, right? So there will be an L shape. So this L shape cannot fill in with 2 and 2. So instead, we cannot use 10 and 0. So we can only use 9 and 4. So the total would increase by 3 is 22. So this 19 is not possible here. But now this says we tried, but we find it's not able. However, so we cannot do does not mean that actually it actually cannot. Maybe just because we are a noob, so we cannot find the actual way to fill it. Can we prove that the 19s cannot work? Actually, we can. Actually, we can. But the proval is a little bit complicated. So I will show you. I will show you. So to prove it, so we should do the coloring with this. So we color these columns. We color all these columns. So then we should have how many grids are here? So totally we have 11, we have 44 blacks. And if you use 9 3 times 3, then each 3 times 3 will just enough to cover 3 of the black grid, right? So each 3 times 3 will cover 3 blacks. And each 2 times 2, it can cover either 2 or 0. So we can say it's even blacks. Let's see. So we have 9 3 times 3s. So we have the total is 9 times 3, then plus an even number times 10, which is also an even number. So the total must be odd. So the total grid, black grid covered must be an odd number instead of even number. But totally we actually have 44 grid. So actually, if we don't want to use the 1 times 1, it's not possible. It's not possible to just use the 3 times 3 and 2 times 2 to finish this work. So actually, this one is not able to do. So we should find the larger solution actually. So we can try this 994. Actually, this can work, right? 22 can work. But actually, 22 is not the smallest because now we think that x equal to 9. So we should increase the number of 1 times 1. But actually, we can reduce the x and replace 1 3 times 3 with 2 of, maybe actually 12 of the 4, 2 times 2, 12 of the 4, and 1 of it. And now here the total sum is only 21. This is possible and the smallest. And the way to fill in this is quite easy. So first, we divided it into, and so see, it's a 5 times 6, right? So first, we use this thing. 11 times 11, right? So we use something like a hypotenuse diagram. So it's a 5 times 6, 5, 6, 5, 6, 5, 6, and a 1, 1, and a 1, 1 inside. So it's very easy for us to divide a 5 times 6 with 2, 3 times 3, and 3, 2 times 2. So it's just like, how to draw this? So it's something like this, right? 3 times 3, 3 times 3, 2 times 2, 2 times 2, 2 times 2, right? So we can make a 4 of the 5 times 6 and use something like a hypotenuse diagram, to fill in. So now the answer is the 21 instead of 19 or 22. They're very similar. So the extremum in theorem is not exactly extremum in actual. So we should find, so if we are able to construct it, that's it. Okay. Then be back to the question. We have 3 questions remaining. So the question 46 is the extremum value in calculation. So actually, we have, right, so 1,965 cards, and we want to put them in 655 boxes. So the sum of the cards in each boxes is different, and the minimal sum is A. We want to find the maximum value of A. So actually, this question is about to make the minimal value being maximum. It's a very paradox exploration, but here's some difficult MM questions. So 4 cases, we want the minimum being the minimum, minimum being the maximum, maximum being the minimum, maximum being the maximum. So for this, minimum being maximum and maximum being minimum, so the strategy is becoming most the average. So we want to set all these numbers. So all the numbers in all the boxes be as average as possible. So in this case, we can make the minimal value maximum as well as the maximum value minimum. So how to make the most average way? We just make them into, because they're different, we make them into the consecutive numbers, then we'll be okay. So first of all, let's calculate the average, right? We calculate the average. So the average, so actually it's the sum of all divided by 655. So we calculate the sum divided by 655, which is the Gaussian sum. So it's 1965, 1966. Thanks God that. So 1965 just 3 times 655. So actually we can just doing this. Right. So the answer then would be calculator. Two, 9, 4, 9. Yeah. So the answer would be the 2949. So this is the average of all. So how to make it the average? So actually, we have 655 boxes. So maybe you arrange it into A1, A2, A3 to A655. Okay? Yeah, we arrange it in this way. And then, so the key point is, what's in the middle of it, right? So the middle term, right? So the middle term is the 655 plus 1, then divided by 2. So it's 328. Actually, the middle term of all is the 328th term. So actually, we may just put the average, right? Because for arithmetic sequence with odd terms, the average is just equal to the middle term. So in the middle, we set the number to be equal to the average. There's 2,949. Okay, and then we trace it back to the A1, which is the smallest, it's A, right? So if the most average makes it into consecutive numbers, so we just use this to use this 2949 to minus the 327. So the smallest, the maximum for the minimum is the 2622. So this is the answer. So actually, so there's so many ways of constructing, so I just give you the construction part. Yeah. So this is the extreme value in calculation, is the MM problem. So I write it here. So this is called the M maximum or minimum MM problem. So minimum, maximum, maximum, minimum. So we use the most average strategy. So maximum being maximum, minimum being minimum. So we use the most extreme strategies. So these are the way to solving this type of question. Okay, then question 47. So this is called a weight problem. So the weight problem is that we want to make use as least waste as possible to measure all the concept numbers, from, for example, 1 to 100 or something like that, right? So how to design the weight of the weight? Yeah, so this is something very tricky. So we use weight to weight the weight, right? So this weight here, so maybe we use the mass, right? So we use weight to weight the mass. So now this weight is a noun here, right? Then it's a noun here. So it's the thing we use to measure the mass. Okay, so maybe we use weight to measure the mass. Yeah, so there's only one weight here. Yeah, much better. So how to set the mass of this weight, right? So how to set the mass of this weight to ensure that we can use this to measure all the numbers between 1 and 100, all the consecutive numbers. So the principle of it is that so how to make it happen? So we just need to make each weight have a weight no greater than the sum of all smaller than +1. So if there is no limitation, the most efficient way so we first we need 1, right? And then we can add in a 2, because 2 is 1 plus 1, so we can measure 1 and 2. So 1 and 2 can measure 1, 2, and 3. So then we adding a 4. So 4 plus 2 plus 1. So we have a 4, so we can use 4 to measure 4, 5, 6, and 7. So the total sum is 7, then we set up an 8. So 16, 23, 64. So this is the most efficient way. This is the 2 to the power of n. So this is the most efficient way to measure all the numbers between 1 to the 2 to the power of n. So actually, because 100 and 1 to 100 here, right? So we only need 100 is smaller than 128. So actually, only 7 is enough to measure 100, right? 7 is enough for 100. So if we only use 7, we use this strategy. But now here is more tolerant. We can use 8 masses. So if we can use 8 masses, so but we want to find the minimum weight for the heaviest mass. So the heaviest, right? So the heaviest may not reach the 64, right? Because we can borrow another one to help us, right? So how do we do this? So also, we use the same strategy here. So for example, yeah, we just keep the first, right? So we have 8 to use. So for the first few, we just keep the same strategy. We use the 1, 2, 4, 8, and 16. So we use 1 to 16. We can measure all of the 1 to 31, right? So now, yeah, instead of use the 32 and 64, for the remaining 3 masses, we just want to ensure, right? So the sum of them not smaller than 69, then will be okay, right? So because now 1 to 31 is already consecutive, so we just need to set the total sum is over 100, no smaller than 100. Then you'll be okay. Because now each number is consecutive, then we just make the sum over 100, then we'll be okay. So we want the last 3 have a sum no less than 39, and we want the maximum, right? See the maximum being minimum. Also, we should use the most average way. So we set the remaining 3 as average as possible. 23, 23, and 23. So actually, this is the most efficient strategy. So we keep the first 5 the most efficient way, but the remaining 3 in the most average way. So can it be? So what if we just, right? So can we, right? Instead, can we just keep only the first 4 to be the most efficient? No, because if you use the first 4, then it's only reached 15. And the sum of remaining is 85. So each must at least be 21, 21, 21, 22. So now here, 21 is larger than 15. So we cannot measure 16, 17, 18. So not possible if we only use the first 4 as the most efficient way. So we use the first 5 in the most efficient way and the last 3 in the most average way. This is the best way for us to find the minimal value of the heaviest mass. So this is the weight problem. Also a type of MM problem. The maximum being minimum. Okay. What's the answer for question 40? So why keep repeating ask the answer for question 44? You have to show it. I have to show it. The question 44, the answer is 9. The answer is 9. Okay. So now to the question 49. Yeah, question 49. So this question actually is not an RMO question. So actually, this question comes from the SMO Junior, right? But I think it's easy. So the primary school student is also able to solve it, and it may happen in the actual RMO. So I put it here. So anyway, so how many numbers can be taken from all the 1 to 2023? So among all the stacked numbers, no number is equal to the product of 2 other distinct numbers. So we want to make sure that I don't know. Why is that? Why is that? Why the so lag for my YouTube? So now, yeah, if we are treating to how many numbers to put in, it's a little bit complicated actually. So let's change this question into another form. So we want to take as most as possible. So maybe we just try to left behind or take it out, right? So we change the question into another form, which has the exactly same meaning, which is how, or at least how many numbers to be removed. So to make no number, or maybe just no production or no multiplication relationship. Or maybe to break up, right? So maybe I use a word to break up all the multiplication relationship. Okay, yeah. We use this expression. Isn't it exactly the same meaning as the original question? Obviously, yes, right? Okay. Then, how to solve this? So we want to break up all the multiplication relationship. For example, we have 2 times 3 equal to 6. 17 times 17 times 19 equal to 3 to 3 or something like that, right? So there are so many multiplication relationships. So we should at least remove one numbers in each of the existing multiplication relationship. So now here's the logic. So which number, we want to remove at least the number as possible. So what should the number be removed? The small number or the large number? So it's quite obvious that we should remove all the small numbers. Why? Because the smaller the number, the more multiplication relationship is involved. For example, 2, yeah, 2 can be 2 times 3, 2 times 4. So not 1, right? So no 1, because it's 1 equal to another 2. So we ignore the 1. 1 can exist. 1 can exist, never mind. So 2 times 3, 2 times 4, 2 times 5, right? Until 2 times 1, 0, see, 1, 0, 1, 2. Yeah, 1, 0, 1, 2, right? So 2 is involved in this. So see 1010, right? So 2 is involved in 1010 relationship. But for larger number, for example, maybe the 100 is only involved 100 times 2 and 100 times 20, right? So 100 is only involved in 19 relationship, because the smaller the number, the more it's involved. So we remove the smaller number will help us to break up as many relationships as possible. So then we start to remove two. Remove 2 will be okay. No, we still have something, right? We have 3 times 4. So we remove 3, remove 4, remove 5. So let's check if this number is removed. The production of the remaining smallest numbers, does it exist, right? So 6, we still have 6 times 7. So this thing happens. So we remove the smallest numbers one by one. And if there is existing, we then remove another smallest number. So this thing would happen as long as we remove the 44. Maybe the 43, right? So after remove the 43, there is still 44 times 45 remaining. So we should at least remove them one, remove the 44. We should notice that after we removing the 2 to the 44, right? So now the remaining numbers are starting with, so the remainings is 45 to 2023. So let's see that. So in this process, so the smallest production is 45 times 46, which is over 2023. But 43 is not, because if we remove 43, there is also 44 times 45 equal to 1980, smaller than 2023. Because we should remember 2023 is very close to the 44 square and 45 square. This is a very important number we should recall, right? So now, yeah. So after we remove the 2 to 44, all the smallest numbers, and then the existing numbers, the smallest product is already over 2023. So there is no more production no more multiplication relationship exists, right? Because all the existing multiplications, the production is already over the 2023. So actually now this works. So actually, how many numbers we removed? So actually, we have the 43 removed. And then how many left? So we have 1980 remaining. So at least the 43 are removed. So at most, 1980 are remaining. So the answer would be 1980. Right. So if it is a short answer, so actually the original is short answer. So actually we get it already. So this is the answer. So we just follow strategy to remove all the smallest numbers because it's involved in most of it. But now we just give, so this is called what? So this is called the extremum in actual. So we have formed the situation that only 43 number removed can make it happen. But can we prove that the 43 is the smallest or the 1980 is the largest? So can we prove it? So is there any other way, right? Is there any other way? Maybe not remove the smallest number. Maybe start with sum of the large number and sum of the small number. Or maybe we remove the middle numbers. So can this thing happen? Is there any strategy, other strategies to make it smaller? It seems no, but how do we prove that there's a no? So actually, we can use the pigeonhole principle. Yeah, we can use the pigeon, or maybe the worst scenario to prove it. So I will write a short here. So how to prove it? Proof is that, so maybe we just select sum of the multiplication relationship, which is, so the number is not choose randomly. So you will see, so what's the relationship of this? It's 2 times 87, 3 times 86, 4 times 85, and 43 times 46, 44 times 45. So now, just based on the 43, just based on the 43 smallest numbers, we find a production relationship with another number. So we know they have the constant sum, right? So the sum is constant. So the sum is constant, which means, right? So they must all have so the sum is constant, then the closer the number, the larger the production. So which means, this one, the last one, must have the largest production. Larger, 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 right? And the largest of this, so this is smaller than 2023. Which means we have 43 different groups, 43 different relationships. And we need to break up all the 43 relationships to be broken. And in each relationship, the product are distinct, the factors are distinct. So we should remove at least one number among each of the relationship. So then at least 43 numbers from each of it to be removed. And then the question is solved. So we prove that we should remove at least 43 numbers. And actually, we have an actual way to just remove 43 numbers. So 43 will just be the, so this is the extremum in fact, this is the extremum in theorem. So they are equal means question solved. Okay, now that's the end for today. All the questions about the combinatorics. I mentioned before, combinatorics is a little bit complicated. And also, right, so It's not that often occurs in the first round of RMO, but it's second round. So now that's all for today. Also, there's broadcast that in this Sunday, right? In Sunday evening, we will have a last class before RMO. So in that time, so I will tell you some strategies in the RMO answering. So how to arrange your time. So how to choose the strategy for order the questions, and RMO is MCQs. So how to get the correct answer even if you don't know how to solve the question. Okay, then okay, enough for today, and see you Sunday evening, and I hope you will get a good grade next Tuesday. Okay, that's all today. Bye.